Our next example is to solve the initial value problem y prime minus y equals 1 plus t e to the t, y of 0 is equal to 0, using the Laplace transform. I'd like for you to write down the result of applying the Laplace transform to both sides of this equation and then come back. The transform of y prime is s y of s minus y of 0. The transform of y is uppercase y of s. The transform of 1 is 1 over s. And the transform of t e to the t is the transform of t, so 1 over s squared, except that e to the t gives us a shift. So we have 1 over s minus 1, the quantity squared. Since our initial condition is y of 0 is equal to 0, I can replace y of 0 using 0. And we end up with s y of s minus y of s is equal to 1 over s plus 1 over s minus 1, the quantity squared. It's difficult to tell you whether or not to combine the fractions on the right-hand side, except to say in this case, I'm not going to. The reason is on the left-hand side, we can factor out the y of s and we get s minus 1 times y of s. The right-hand side remains unchanged, and you can see that we're going to have a couple of fractions. We're going to divide by s minus 1 in order to isolate y of s. And so y of s is equal to 1 over s times the quantity of s minus 1 plus 1 over s minus 1, the quantity cubed. That is easily transformed using the shift here. For 1 over s times s minus 1, I need to use partial fraction decomposition on that. You could combine these into one single fraction and use partial fraction decomposition for the whole thing, but it's a little bit more cumbersome than doing what I'm doing in this case. Again, how do I know when I'm going to do that, when I'm not? Kind of take a global view and see, do I have something that's like ready-made for me, and then just deal with the other part. As for that other part, 1 over s times s minus 1 decomposes into a over s plus b over s minus 1. And you can confirm that a is going to turn out to be negative 1 and b is going to be 1. Therefore, y of s is going to be negative 1 over s plus 1 over s minus 1 plus the untouched 1 over s minus 1, the quantity cubed. This would transform to a t with an exponent, and we note that with that denominator having a cubed in it, n is equal to 2. Therefore, for that term only, I need to multiply and divide by 2. I'd like you now to apply the inverse transform to both sides and solve the differential equation. I'm hoping you got y of t is equal to negative t plus e to the t plus 1/2 t squared e to the t. I actually do hope that you got that. Next up, we have 2y double prime plus 20y prime plus 51y equals 0. Y of 0 is equal to 2, and y prime of 0 is equal to 0. I'd like for you to apply the Laplace transform to both sides of this and get to the point where you have y of s is equal to, and then come back. We've got 2y double prime. That gives us 2 times the quantity of s squared, y of s, minus 2s minus 0, because we've substituted 2 in place of y of 0 and 0 in place of y prime of 0. Next term, 20y prime, gives us 20 times the quantity of s times y of s minus 2, again because we've substituted 2 in place of y of 0, plus 51y of s is equal to 0. I've distributed and collected like terms and then divided, giving us y of s is equal to 4s plus 40 over 2s squared plus 20s plus 51. If you don't already have it in this form, then make sure that you are following along, and we're going to move on. I had you stop here because what to do after here, it's a little bit difficult to anticipate what to do next. But we don't have anything that tells us how to deal with a factor like 2 in front of s squared in the denominator in order to find an inverse transform. So what we're going to do is we're going to multiply numerator and denominator by 1/2, thereby giving us a clean s squared term in the denominator. That gives us 2s plus 20 in the numerator, and in the denominator we have s squared plus 10s, and then, dividing 51.5 would give us a fraction, but it's actually 25.5, so I'm going to write it down as plus 25 plus 1/2. And the reason for that, folks, is that the s squared plus 10s plus 25 is a nice perfect square. So we have that y of s is equal to 2s plus 20 divided by the s plus 5, the quantity squared, plus 1/2. Now it's time to interpret what we have in terms of inverse Laplace transforms. That s plus 5 in the denominator tells us that we're going to have a shift, and I'm going to be looking for an e to the negative 5t in our answer. Again, in the denominator, that plus between the two terms tells me that we're dealing with a sine or cosine, and in fact, in this case, it's sine and cosine. And when we consider that sine and cosine, we have this plus half. That's telling us that k is equal to 1 over the square root of 2. There are multiple ways to proceed from here, so this is only one possible path. I'm looking at this numerator, 2s plus 20. We have a thing squared plus thing squared in the denominator. Like I said, that's going to give us sine and cosine. The existence of an s in the numerator tells me I'm going to have a cosine. The existence of a term, that 20, that doesn't have an s tells me that we're going to have a sine. So I'm going to split this whole thing up. I'm going to factor out the 2 from the first fraction. I have 2 times the fraction s over s plus 5, the quantity squared, plus 1/2. And then we have plus 20 over s plus 5, the quantity squared, plus 1/2. In both cases, the s plus 5 is giving us a shift of e to the negative 5t in our answer, but that shift needs to be reflected everywhere we see the s, which means I also need it in the numerator of the term that has the s. I'm going to add 5 to that numerator, but considering the 2 that we have in front of that fraction, what I've really done is I've added 10 to that side of the equation. In order to offset that, I'm going to subtract 10 from that side of the equation in the form of subtracting 10 from the numerator of 20. The only place that the k equals 1 over square root of 2 will appear in the cosine answer is in the argument. For the sine, though, we need that k in the numerator. So I'm going to take that 20 minus 10 and multiply and divide that by 1 over the square root of 2. And the reciprocal of 1 over the square root of 2 is simply square root of 2. We're ready to write the answer here, folks. Y of t is equal to 2 e to the negative 5t for the shift times the cosine of 1 over the square root of 2t plus the square root of 2, it should be 10 times the square root of 2. I almost lost that 20 minus 10 in the numerator. E to the negative 5t times the sine of 1 over the square root of 2t. Now we're going to look at a boundary value problem, y double prime plus 8y prime plus 20y equals 0. Our boundary conditions are y of 0 equals 0 and y prime of pi is equal to 0. The formulas we have for transforms of derivatives involve y prime of 0, not y prime of pi. So we're going to let some constant c, whatever you like, equal y prime of 0. It'll be a placeholder that will allow us to find the transform, and then we'll find the value of c by using y prime of pi equals 0. Well, I said we, but what I want you to do is take this problem as far as you can, see if you can solve it all the way, and then come back. Transform of y double prime is s squared times y of s minus sy of 0, but that's 0, minus y prime of 0, which we're calling c. For 8y prime, we have 8s y of s. Again, y of 0 is equal to 0, and 20 times y of s equals 0 is the rest of our equation. Factoring out the y of s terms from all the terms that contain that, we get s squared plus 8s plus 20 times y of s is equal to c. And so y of s is equal to c divided by s squared plus 8s plus 20, and I'm expressing 20 as 16 plus 4. So that becomes y of s is c over s plus 4, the quantity squared, plus 4. We have a constant numerator and a sum of two squares in the denominator. That's going to give us a sine inverse transform. We notice that k is equal to 2. So I'm going to multiply and divide by 2. And then apply the inverse transform. We have y of t is equal to c over 2 times e to the negative 4t from the shift that we have in the s plus 4 quantity squared in the denominator times the sine of 2t. Ordinarily, I would change the constant c over 2, but we're about to replace it or solve for it, so I'm not going to bother. We have y prime of pi equals 0, so I need the derivative. I've factored out the c over 2 and used the product rule, negative 4e to the 4t sine of 2t plus 2e to the 4t cosine of 2t. Substituting pi in place of t gives us 0 for the sine of 2t and 1 for the cosine of 2t. Ultimately, that gives us that 0 is ce to the negative 4 pi, and since e to the negative 4 pi isn't 0, c is, and since c is 0, our only solution is y is equal to 0. This only has the trivial solution.